this last slide about the introduction of the institute, we have a center of doctoral training where we are training PhD students. We have a lot of funds available, a lot of opportunity in case some of you is interested or some friends want to do a PhD with us. Right, so let me move with introductions. As I mentioned before, so what we do nowadays is using virtual prototypes to develop a new structure, a new material, and these prototypes are numerical models, and they are very accurate, and the deterministic model is actually quite complex. It takes a lot of time to be evaluated. But the problem, the models are deterministic. There is no much uncertainty considered in the model itself or on the parameters that can be random and can be affected of stochasticity. And as you know, that the random effect can have some very nasty consequences. So it's really important to look for the black swan. Right, and so which are the questions that we need to answer? First, we need to know how to model the uncertainties, how to characterize the uncertainties, and this is answered by uncertainty characterization. But here we are focused more on how does the uncertainty propagate to the model? What is the effect of uncertainty of the quantity of interest? And this is answered by the uncertainty quantification. And today I'm going to explain the different techniques that can be used in order to answer this question, the uncertainty quantification. There are different challenges. The first, I already mentioned, the models are complex. It takes a lot of time to evaluate the model. For instance, you need to evaluate performance analysis of this satellite. It might require few hours. So if you do stochastic analysis, you need to repeat this 1 million times. So that becomes infeasible. You need to do something more efficient and to use some smart techniques. Of course, you can use high performance computing. You can parallelize, well, but you have the limitation of the licenses. You don't have an infinite number of licenses. And also, but fortunately, you can use advanced simulation methods, not only plain Monte Carlo techniques. Right, and so just a brief introduction, the definition of reliability analysis. This is what we are talking about here. So this is our interest, is basically is the probability. So we need to estimate this integral where f of x or dx is represents the failure probability density function. That is another important component that has been already introduced, so that it can be very fast. Here is the so-called performance function. This is simply a function that is split the input space here into different regions where everything is under control. We are in the safe region. Here we are an unsafe region, the failure region. And when this function indicated with the letter g is equal to 0, we call it limit state function. And actually, the estimation of this limit state function is critical to estimate the probability of failure of some component or some structure. Well, so in a structural reliability problem, so we can redefine or rewrite the probability of failure as the following. So basically, we need to evaluate this multidimensional integral, where f of x represents the multivariate. This represents our distribution of the random variables, and this represents the space of integration where you need to evaluate this integral. So there are different tools that can be used. We have approximated methods like form, SORM, and so on. We have a Monte Carlo simulation, and we have advanced Monte Carlo methods like importance sampling, line sampling, and subset simulation. I'm going to explain how can we apply those tools, when you can use one, when you should use another one. I'm not talking about a surrogate model in this talk, but only about direct simulation techniques and also about approximate methods. So these are the questions. I think that the topic of this talk is how can we do, which tool can be used in higher dimensional space, 30, 40, or 100, when we have a multiple failure mode. And so basically, here is we come in the field of system reliability, where phi is not the CDF normal distribution, but is a structural function. So I'm sorry for the confusion. And the third question is, are we able to estimate the small probability of failure? Right. First of all, let's start with the approximate method. Well, this is for normal random variable and linear performance function. So basically, you can define the so-called safety margin. So basically, you can define your limit state function as a difference between the demand and capacity. This is the simplest way. And in this simple case, this is distributed as a normal distribution with a specific mean and variance that can be estimated analytically. No problem, perfect. So that's actually the best way to do it if you are in this situation. You have a normal random variable and linear performance function. So then you estimate your beta values, that is the reliability index. I guess most of you are familiar with that. And this can always be done by, if you don't have a random variable, standard normal random variable, you can always transform the random variable in a standard normal space and use this approach. And you can estimate the probability of failure analytically. So you have the estimation of probability of failure by simply evaluate the phi that represents the CDF of the Gaussian variable. Well, what is the geometrical interpretation of this reliability index? That represents a number of standard deviation with the mean values, which the mean values of the safety margin m exceed 0. That actually can be explained with this nice graph here. So this is the mean values of the safety margin, and the beta represented the distance in terms of standard deviation from this to the limit state function. So basically, of course, the larger the beta is, the more safe the system or the component is. And as mentioned, this can be applied in a standard normal space by means of transformation. You can use NATA for different transformation. So basically, you transform the original problem, so maybe here, in a problem like this, where you computed the beta is the minimal distance of the limit state function to the origin in the standard normal space. Right? So basically, this represents the idea of form. Form is well known, has been developed in the 1974, and so it's very old method and quite easy to apply, right? So the only thing you need to do is to estimate beta. How do you estimate the beta? You find the minimum distance of this function to the original standard normal space. Well, you can see this as an optimization problem as well. And usually, this is solved by calculating the gradient, and then a sort of different iteration, you're able to identify this minimal distance. Right. Can we apply these techniques in our case? Well, in a high-dimensional problem, probably not, because, well, you need to estimate the gradient, or you need to, anyway, to find the minimal distance of the limit state function with the origin and standard normal space. And if the limit state function is not linear, and you are in a dimensional space, it has been proved that the design point has no meaning there. Well, what if we have a multiple failure mode? Yes, it's possible. You can still apply it. With probably relatively simple to do that, and this I will explain later. Can we estimate a small failure probabilities? Yeah, we know, no problem. There's no difference to estimate a failure probability or calculate a beta equal 1 or a beta equal 5, 6, 7, or 42. Right, and now, but there is a completely different approach, is simulation techniques, and the first is the Monte Carlo method. So Monte Carlo method is general numerical model that allows us to estimate defined integral. You can see here f of x and dx represent the probability density function, and g of x the function that we need to integrate. And you can prove that using Monte Carlo you have an unbiased estimation of the values of g. And in our case, basically what we need to do, so for instance, here we have again demand and capacity. you need to calculate the convolution of these two functions. This way can be rewritten in this integral. And using the indicator function that already been introduced in the previous talk, so we can estimate this integral by means of Monte Carlo. Basically, we generate random realization from the proper distribution, and we count how many times we have samples in the failure space, and we divide by total number of samples. So basically, this is your estimators, and this is based on the the method called DART method. Basically, we generate realization from the underlying distribution of the random variable. We evaluated model. For each model evaluation, we identify the values of this indicator function. This is 1 if we are in the failure domain. And we calculate how many times we collect the values of this indicator function, and we divide by total number of simulation. This approach is always working. Always. There are no limitations. You can calculate any integrals. So provide the exact solution if you use an infinite number of samples. So there is no approximation here. So absolutely, you have the exact solution. Does not require any prior knowledge. So you can apply directly without thinking much. Of course, we have a problem, the accuracy of the estimator, because this has been shown before. The number of samples depends on the number of the values of the probability of failure you want to estimate. So of course, if you want to estimate the probability of failure 10 minus 8, well, you need 10 to the power 9 samples at least. And so this becomes infeasible for expensive model and low probability of failure. But if you have a surrogate model, then probably the best way is to apply direct Monte Carlo on top of surrogate model. So just to answer the question, so can we apply in higher dimension? Yes, without any problem. Monte Carlo is independent on the number of the dimensionality of the problem. Can be identify multiple failure mode? Yes, with no problem. So actually, this is the only method that guarantees to identify all of them. Can we use Monte Carlo simulation for this estimation of small failure probability? Well, usually not. There are a few exceptions, as I mentioned before. If you use a non-expensive model, or if you use a surrogate model, then you can still do it. And in my opinion, it's much better to apply direct Monte Carlo model on top of surrogate model than using anything else, because then you add an approximation on top of another approximation. Right. One method to reduce the variance of the estimator is so-called the importance sampling. And this actually was the topic also the first talk. So I go a little bit faster here because I don't need to explain all the details. So what's the main problem of Monte Carlo? So for instance, so if you generate sample according to f of x indicated here, but you need to evaluate the function indicated g or x, so you have a lot of samples here. Sorry, a lot of samples here when the values of g or x is very small, and few samples here where the values of g or x is very large. So you have probably 100 numbers, as they will always be close to 0. Then suddenly you have one number, it might be 1 million. And this variability will destroy your variance, the variance of the estimator. So the best way is instead to generate samples from f of x, generate samples that are very close to g of x. And it's been shown before that you can identify the optimal density function, where you need only one sample to estimate the probability of failure with the variance equal to 0, but it's as difficult as to estimate the probability of failure. So in practice, this is not possible. But what we can do is, instead to generate a sample from f of x and dx, we generate from a different distribution indicated here with f1 of x. And then, in order because we don't want to change the values of this integral, we need to divide by f1 of x. So what we do, we generate samples from this distribution, f1 of x. In this case, we collect the price, and the price is not only g of x, but it's actually g of x divided by f1 of x. And the estimator is basically the estimator of this new function indicated here with G1. So instead to collect 1, the indicator function, as in the plane Monte Carlo, we collect the values of this new function. So there is also another way to show. And for instance, let's assume we want to estimate the probability of failure in a very simple case, where the probability of failure is defined as the probability to exceed these values here. If you generate using plain Monte Carlo, we generate a lot of samples here. But if you move this distribution, if you use this new one, most of the samples are actually now in the failure region. And you can see here the same concept in 2 dimensions. So the probability of failure can be the estimator of the probability of failure is like the previous case. We have the indicator function that's equal 1 where we are in failure region, but this time is multiplied by the weighting factor. And this weighting factor takes into account the fact that we are sample from the proposal distribution, this one, or important distribution, and not from the original distribution. We need to take into account the fact that we are somehow cheating a little bit. Well, which are the advantages and disadvantages of the important sampling? First of all, so you need to know where the failure probability is. If you know more or less where the probability of failure is, well, you can construct a distribution that's around that area. And one way to do that is basically to use a design point, and this has already been shown before. You can use the information design point to construct an important distribution. So in higher dimension, is possible? Well, that's, as was shown before, there are some limitations, but yes, it's difficult, but it's possible. You can even sample in higher dimension. The problem, Bruno mentioned that in case of very large number of dimensions, probably not all of them are important. So you can define important density that take care about only the important components only. Right, so multi-failure mode, yes, this is possible, and I'll show you later when I'm talking about that specific problem. Can we estimate a small failure probability? Yes, that's actually the advantage of the important sampling. The other topic, so other method I would like to present is so-called line sampling. This basically is a method based on linearization of the limit state function. This is actually like form. So line sampling can be seen like a weighted average of form. So it's like a way to repeat the form analysis many times. Well, so how does it work? Here a little bit of math. Doesn't want to explain in detail, but the probability of failure can be written in this way when each fan represent. We are working in standard normal space. Everything is a Gaussian uncorrelated random variables, and as you know, it's always possible to map the real physical space in a standard normal space. So this is a multivariate normal distribution. So we are in standard normal space. We can rotate the axis. We can rewrite this integral in this form, where this U1 can be interpreted as an important direction point towards the failure region. So this is another way to rewrite this integral. And we can see that the integral can be rewritten in such a way where you have these weights here. And these weights actually are calculated by solving this. Actually, if you see here, this is actually form. So where C is basically your beta values. And so basically you calculate the values of these weights. They can be used at the smallest values, where alpha, this is actually the direction pointed towards the failure region, where the indicator function steps from 0 to 1. So exactly in the limit state function. So this weight is a measure of the likelihood of the variable that is orthogonal to the important direction to be in the failure domain. And then we collect all these basically weighting factors. So basically you can see here is an average of form. Let me explain graphically the concept of line sampling. So first of all, we identify a direction alpha. So we have a direction pointing towards the failure state, the failure region. So then we generate samples in the hyperplane perpendicular to this alpha direction. And for each point in this hyperplane, we generate some lines orthogonal to this plane. So, and then we identify the intersection of this line with the limit state function. And this can be done by evaluating the model a few times along this line. And then what we do, we compute the first order ability for each line that corresponds to each line. So basically we compute form here, form there, and we average the results. Right? So which are the characteristics of this technique? Is a really efficient approach, and the number of samples required are independent of the failure probability level. So you can estimate the probability of failure 10-2 or 10-8 with the same number of samples. And it's very efficient in higher dimensional space, but you need to know the approximate direction, this important. You need to know this important direction or an approximate values of this important direction. This is a quite strong limitation. It doesn't work well if you have strongly nonlinear performance function. So you cannot solve all the problem, but in most of the problem this can be applied. There is also some advancement on line sampling that's called advanced line sampling for a reason. So first is to reduce the number of model evaluation. First we can use smart method to estimate the intersection point with the limit state function when we evaluate points along different lines. Then we, instead to estimate the points along the line randomly, we first identify the intersection of one line. Then we identify the closest point to the previous line, and then we evaluate again the intersection point. But this time starting from the same distance as the previous one. This because usually the failure region has no crazy shape. So it's most likely that you are already very close to the limit state function in this way, because these two lines are very close. So basically you can use the same distance of before to start searching for the new intersection. In some cases, with only one sample, while model evaluation, you're already very close. So that actually saves a lot of space. And then you process the next line. The second advancement is what happens if we don't have a good important direction? For instance, you might have first this important direction here, and we generate the lines here, and we identify intersection. Then we evaluate another line, and we find another intersection. And then we realize that actually the distance of this point from the center of standard normal space is actually smaller than this one. That means this is the real design point, it's not this one. So, well, what we can do, so we have done some analysis using the wrong direction. That's no problem, because we can simply rotate all the space, and so we are in standard normal space, so all the points are invariant to the space rotation, and we can reuse the point evaluated in the previous analysis also when we have rotated and we have updated the values of the important direction. So this actually is a quite a smart idea, because you can basically guess the important direction, starting analyzing, evaluate the model along some lines, but then when you realize that you have found a better direction, you can remap all the points and reuse all the previous analysis to have a better estimator. So, so this has been proved from the different examples. This is the first example, very simple example. So and here's a comparison of Monte Carlo line sampling and advanced line sampling. So first of all, it fits, so it's able to calculate the right probability of failure. And when you change the value of C, and C represents the it's proportional to the probability of failure, we can even compute the probability of failure 10-7. And the required number of samples for line sampling is always constant. It is actually quite good. So you can use the same number of samples to estimate the probability of failure 10-2 or 10-7. So that's actually the beauty of these techniques. What about the number of variables? So basically scales quite well. So of course you need a little bit more samples when you increase the number of variables, but actually, well, with less than 1,000 samples, you can basically analyze problem up to 500 dimensions. So it's quite efficient. And you can see here, obviously, Monte Carlo is always the same number of samples because it's been said many times is independent of the dimensionality of the problem. Right, and we have done some application. There are a lot of publications produced where we have used line sampling to estimate the probability of failure of real systems. Like this was a building modeled in Abacus with 8,000 elements, 244 independent uncertain random variable considered, and with only 100 model evaluation, we were able to estimate the probability of failure on the order of 10 minus 5. So it was really efficient. And in this way, you can apply this method directly without using surrogate model. Because the 100 model evaluation is what you need usually to train your surrogate models. Well, can be applied for high dimensions? Yes, we can. You can have a look on this paper. Can be applied for multiple failure mode? Yes, it's possible. I will explain later. And can be estimated a small failure probability? Yes, of course, you can do it. The last technique I would like to present is subset simulation. Well, I don't need to say much here because it's already been covered. But as you know, that the idea of subset simulation is to estimate the probability of failure as a product of a conditional probability here. So we generate samples from initial samples, then we define intermediate failure probability. Well, there are different rules. You can estimate this one, and then starting from these samples that are in the failure region, we can generate using different techniques and algorithms new samples, and you estimate the next intermediate level until you reach the true limit state function. Right? Of course, there is a lot of discussion how to generate these samples. There are different techniques like Markov chain, and that's the most popular one. So there are some requirements, some challenges in a subset simulation. So first of all, how to generate conditional samples. That's actually the big question. So there are different techniques. So I've now proposed to use the Metropolis-Austin algorithms, the component-wise update. So basically, because this solves the problem of the dimensionality, while if you use the traditional Metropolis-Austin algorithms, you have some problem when you work in a high-dimensional space. And this somehow the algorithms of the classical implementation of a subset simulation. And then has been recently we have been proposed a variant of subset that we call a subset infinity. This actually have been introduced before because this approach has been identified independently by two different groups. So, but the concept is the same. Right. So the idea is let's try to understand the performance of subset simulation where the dimensionality of the problem increases. And we know that the subset simulation works quite well in a dimensional space. So the idea here, let's replace each variable as a sum of, in theory, a possibly infinite number of hidden variables. We can do that. Each variable is a sum of hidden variables. And then we can, again, study the limit behavior of the MCMC algorithms. So what we have done is simply replacing each variable as a sum of a number of hidden variables. And then we have applied the traditional MCMC algorithms. So studying the behavior of these algorithms has been proved that actually the candidate samples are distributed as a Gaussian distribution with mean indicated here and a specific variance. Right, that's nice. So we know that the candidate samples are distributed according to a Gaussian distribution. So the idea here, let's generate them directly from a Gaussian distribution. It's much more simple. Because actually, we have a relationship between A and S that represent control the mean and the variance of this distribution. So basically, we have only 1 degree of freedom, so we need to select the values of one of these parameters, and then we have automatically the other one. So it's been proved that the conditional PDF does not depend on the number of hidden variables, and this allows to generate samples directly from a Gaussian distribution. So this is simple. The code, so for each level of subset simulation, you generate the sample from a Gaussian distribution, and then you accept or reject the samples using the same rules, these are classical rules of subset simulation. Well, if you want to implement this code, there are 5 lines. These are only 5 lines of code that you need to implement, and this is MATLAB. Of course, there is all the loop around, but it's a 5-line of code. And these are here. So you just copy and paste, and this you have it. And I mean, actually, this is the beauty. It might not be perfect, but it's so simple to implement. It's so simple, and you need to control only one variable. Right. So, of course, there is this magic parameter here. This the values of this variance of the distribution. So you can study the behavior of the of subset simulation, changing the values of this parameter. S has been found that actually using 0.5 produces the smallest variance of the estimator. It's like which is the intermediate level of subset simulation you need to use? The answer is always 0.1. This has been also proved that actually is the optimal selection, but it's also another magic parameter of subset simulation. Right, there are some benchmark examples presented here. As you can see, there are always the same benchmark example presented by all of us, and it's actually quite nice. We are testing our code on the same problem. And well, so how does it work? So you generate samples, the initial samples. So you identify the intermediate level here. So basically, only this sample will basically exceed this intermediate threshold, and from these samples above this threshold, what you do, you generate the candidate samples from a Gaussian distribution with a specific mean and standard deviation as defined before, and then you reject these samples because they are above, or in this case below the limit state function, and you keep all the others, and you repeat this analysis for all the other levels until you reach you identify the real limit state function. Is actually when the values of our g function is negative. Well, actually, 0 is the limit state function. When you find the intermediate level is negative, means that you already exceeded that. So you stop your algorithms. Right, I think I still have 5 minutes. Huh? That's pretty nice. Because I want to discuss a little bit about what do we do when we have multiple failure modes. That's probably the interest of most of us. Right, and so there are different ways you can address a problem. So for instance, let's say we want to analyze the failure of this simple system. So if you're a civil engineer, probably you know the solution. There are different failure modes, and these are different failure modes, right? So there is a complicated way to address this problem, and there is a simple one, and I want to show you the simple one. So each failure mode actually, if known, can be analyzed separately. You don't need to put everything together and to have a crazy limit state function. You can simply analyze each failure mode individually. And then you compute the failure probability of the system, the total failure probability, as a combination of events. So basically, it's just to reduce your problem as a combination of AND OR gates, basically. So you can definitely write, for instance, a fault tree for the failure of this system. And what you need to do is to calculate the probability of the failure of each individual failure mode. That's much more simple than estimating the probability of failure of the system. And well, so divide, make a problem simple, and you will be able to address. So as I mentioned, each failure mode can be reduced to a combination of parallel and serial system, all of them. Well, then what you can do, you can use a polynomial fitting to try to fit a crazy shape of your limited state function, like proposed by Gregorio, or you can use a product of conditional margin. You can use bounding techniques to combine the different probability events that are shown here. And this is actually how to calculate the upper and lower bound of this combination of failure modes. And this some relevant papers, right? But as I mentioned, so you can reduce the failure mode you can analyze as a system reliability analysis, and you can apply the techniques I presented before to analyze each failure mode, because only Monte Carlo sampling guarantees the identification of all the failure modes. There is no other way, unfortunately. So, for instance, you can okay, let's assume our system can fail in a combination of event A and C, or a combination of B, C, and D. So basically, this one is a failure region, this is another failure region. And there is all the combination of the possible failure modes. You can create an important sampling here, because you think it's the failure region, but you are neglecting this area. Or what you can do, I can create 5 different important sampling density and estimate the failure probability associated to each failure mode. And you can do that. And there is also a nice way where you have been introduced in this paper, where you can instead to generate samples around the design point, but spread it out, you can actually concentrate all the samples only in the intersection of 2 events. And okay, there's not time, so I don't explain this one, but what I want to show here, you can, for instance, using line sampling as well. And line sampling, you can apply line sampling to estimate the failure probability of each individual event. So, and they're almost linear, so actually you don't need so many samples. 2 or 3 samples you can estimate, even form, because you can use a form to estimate the probability of failure of the first mode, failure probability of the second mode, and you simply need to combine the different events. You can also use subset simulation. Subset to estimate the probability of failure of each individual failure mode, or if you want to use subset to estimate the probability of failure overall system, you can do it, but there is no guarantee that you cover or you be able to identify all the failure modes. Well, what I want to say is, when you're talking about multiple design points, well, there is no way you know that there are multiple design points. Either you do Monte Carlo or forget it. I mean, if you know there are multiple design points, just address them separately. It's much more simple. Okay, just in conclusion, so this is an overview of the tools presented. There are different analytical approach, but they are limited to quasi-linear cases and low dimension, usually, but are independent of the value or the probability of failure. Monte Carlo method is the method that you should apply in higher dimensional space if you can afford to perform a lot of samples. Important sampling requires the prior knowledge of the important area. Line sampling is independent of the target probability level, but does not work for strong nonlinear performance function. So this is a limitation, this one. Subset simulation is applicable for linear nonlinear case, but somehow it's difficult to tune. And it's difficult to estimate the variance of to calculate the variance of the estimator. You do subset. Do you trust your result? Well, sometimes yes, sometimes no. And so basically, what do we do? In higher dimensional space, you can use Monte Carlo, you can use line sampling, you can use subset simulation. If you have a multiple failure mode, either you use Monte Carlo or you decompose your failure modes. And small failure probability using line sampling or subset simulation. And you can find all these techniques and all the examples presented in our software, we are developing another open source tool. It's actually like UQLab. So you have choice, of course, you can use both. There's no competition here. You can use definitely both. But actually, you don't need to recode all the techniques. They're already there. And if something is not there, you can implement a new one and share with us. The last one, so I will hope to see you in Liverpool. This is some advertisement, sorry about that, in July. We are organizing this reliable engineering computing, and the theme of the conference is Computing with Confidence. I hope to see you there. Oh, thank you very much for your attention.